Kelly.
Yeah. All right. So for those of you who chose Ben, explain yourselves. What's your thinking?
Space.
Yeah. So like when we see astronauts in space, what do we notice about them?
They're floating and stuff.
Mm-hmm. Yeah.
There's no gravitational force.
Gravity doesn't seem to be affecting them. Yeah. All right.
So what
Any
about
other reasons?
Well, I know that there's no air in space, and that's why when you go out in space, you freeze. So there must not be an atmosphere, is my guessing. So that's why I thought Ben was right.
No, that's good. That's good thinking.
I thought that so long as there's like a mass of like density so that gravity can pull, I don't think an atmosphere is necessarily the only thing like air does for like gravitational pull, as what my guess is, like slow down like obviously like air, the air, what is it called, like when you throw something air, that's the only thing.
There's like resistance.
So like the only like space is just like there's not like a mass that like gravity is pulling from or anything like that, so that's it.
Yeah. All right. Did anyone go with Kelly? Do you have an explanation you want to offer?
That was my explanation.
Oh, sorry. All right. That was good, Hank.
I chose Kelly because even if like there is no air or atmosphere, gravity never actually reaches zero. So even though the gravitational force may be small, it's still exerted in space. So
yeah, it's just much lower.
Yeah, I said like Kelly because in the equation, like calculating the force of gravity, there was no variable for air or atmosphere. It was mass and distance.
Yep. All right, that's all good thinking. I think this formative assessment probe gets right at that, because our personal experience, we think of, we are in an atmosphere and we experience gravity here on Earth. And what Hank was getting at too makes a good point about how where there's a lot of gravity, there tends to be air, because gravity is actually holding the atmosphere to Earth's surface as well. And Nadia made a good observation that like when you think about astronauts in space, they're floating around. But remember that astronauts are still breathing air. There's air inside their suits. They have an atmosphere inside their, their modules, like inside of the space shuttle or anything else like that. And so it turns out that the more correct answer is actually Kelly. Just to see how the votes came out, though, I want to look at the pie chart here. So it looks like you guys were split almost half and half. It's kind of interesting that most of you went for Ben, less than half for Kelly, but it is Kelly's actually thinking you're right that gravity's present even where there isn't an atmosphere. So that's something we're going to explore more, but that's good to see. I mean, this is not surprising at all because of the way we think of space as, we see astronauts in zero gravity and us experiencing gravity here on Earth. So, all right, the next task I would like you to work on is the Do Now reading quiz. This is task number 2 on the Canvas post for today. Go ahead and click on that. It'll take you to a Canvas quiz. This is open notes. So if you took notes on the reading, either in your Google Doc or on a piece of paper, you can refer to those. I discourage you from looking at your textbook. I mean, I can't check you or stop you from doing that, but the skill here to learn is to take good summary notes. So it's 4 questions. Again, I'll time us for about 3 minutes and I'll just check responses. And again, let me know if you have any questions, but right now I got 3 minutes to work on that. Go for it. All right, I'll have you all unmute yourselves for me really quickly. Yeah.
I haven't voted.
What's that, Kinson?
I haven't voted yet. Should I vote?
Oh, yeah. Go ahead if you haven't done so. Just click on that form. The link is, it's the 3rd task, and you can do that. So, all right, how do we feel about that quiz? Pretty good? Did it work well on Canvas for you?
Yeah. All
right. Let's take a look. I don't know what order you answered them in. First question I get is, why doesn't the moon fall towards the Earth? The correct answer, most of you got, is that it has a high tangential velocity. What does that mean?
It's like potential energy.
I think the moon has a lot of potential energy, but it's more kinetic. It's a form of motion. It does have potential energy by being high up, like it is falling. It is going to fall, but tangential velocity is getting something else.
It means that the velocity that's going at is parallel to the surface of the Earth. So that way it falls around the Earth, not on it.
Yeah, so velocity is movement in a certain direction, and in this case, yeah, it is falling around the Earth, which is a weird way to think of it, but that's what an orbit is, and that's something we'll explore a little bit later. But you're right in terms of the moon does have potential energy as well, being high up, like anything that before it drops. So the next question is this really weird definition about gravitational force where there's two proportions. You have to think about the mass and the distance between the two objects. It is directly proportional to the product of the masses and inversely proportional to the square of the distance, which most of you got. That's a really fancy way of saying that when you express this in math, you put the mass on the top and the distance on the bottom. That's all that's referring to. In other words, as mass gets bigger, gravitational force gets bigger. And as distance gets bigger, gravitational force gets smaller, right? We'll explore that a little bit later. The inverse square law is building on that. So the greater the distance from Earth's center, the correct answer was less gravitational force, right? The farther apart objects are, the less gravity they experience between them. Most of you got that, which is great. And then if two objects are placed far enough apart, the gravitational attraction will reach zero. That is false. Most of you got that. As much as you hear that term, there's actually no such thing as zero gravity. It can get very close to zero, it can get very low, which is why you see astronauts floating around in space. But even in that moment, when it looks like you can let go of a pen and it just floats there, gravity is acting on it. It's just in such low amounts that it doesn't make a seeable difference for us. So these are all things we'll explore, but it looks like you're feeling good after the reading, which is great. Our next task is to reveal who won the vote. So this is which group is going to get the $100,000. And if anyone's reading the tasks, what is the prize for winning?
5 extra credit points.
Giving you some extra credit points on labs. So I can add it to an assignment or just add it to your grade overall. But that's what I've decided to offer. So I think everyone has voted. There are 19 responses, which is more than we have in this class. So I'm not sure what's going on there. I'm wondering if we are having some outside influence on our voting, but either way, let's see. So drum roll. I'm curious to see if this is, oh, all right. Well, there's still a sound winner. So it looks like we had single votes for chemical pollution, eutrophication, and overfishing. Then 2 votes for oil spills, 3 votes for warming seas, 3 votes for ocean acidification. But the resounding winner with 8 votes is plastic pollution. Way to go. Who were our presenters on plastic pollution in this class? John and Luca? No.
No,
Who did
it
plastic
wasn't
pollution?
Matthew.
Wait, plastic pollution?
Yeah, plastic pollution.
Jensen and I.
Oh,
Jensen and I. Oh, okay. Yeah. Yeah. Yes. Those. So that. Way to go. So I'll add that on when I can. But good job to all of you, and those presentations were good. It was fascinating seeing some of the stuff you researched, and you asked some good questions after the presentations. I know we kind of drew this project out much longer than it would have been, but it was a nice way to sort of transition into the online learning, I think. So, we'll continue to touch on environmental issue stuff even as we continue the course, something we've done repeatedly here. So, any other questions or comments on that? All right. I want to move on to our newest unit, which, as you know, is gravity and physics. Bear in mind that I have not ever taught physics before. I've taught chemistry and biology, but this is a new subject for me. So I'll be learning some of this with you guys. But what I want to do right now is just really quickly, I'm going to use just 4 slides to review the key content from the Hewitt chapters. So if you want, you can take notes in your Google Doc or on a piece of paper. But honestly, if you took notes from the reading, then I'm just going to be reinforcing a lot of that. If I ask a question and you want to answer, just remember to unmute yourself, or if you want to ask a question or interrupt me, again, just make sure you unmute yourself and feel free to jump in at any point. And then we're going to do some activities to explore some of the things from this chapter. So the chapter starts off by talking about the apple. Which famous physicist and scientist in general does this story refer to?
Newton.
Yes, and so I knew this story about the apple, but I didn't know the whole thing about it. I always thought that he was just sitting under a tree and the apple fell, and he started thinking about, well, what drew the apple to the ground, and that's what gave rise to gravity. But it actually turns out that when he saw the apple fall, he was also looking at what? What was in the sky?
The moon.
Yeah, and he started thinking, well, gravity must also be acting on the moon with the same amount of force, right? Here's our little happy moon. And so that kind of was an interesting new idea, that gravity was acting on all things with the same, in the same way, and yet you see different behaviors, right? The moon does not fall straight down to the earth, and so we've kind of hinted at why that is already, and I'll explore that in the next slide. But this was kind of the big breakthrough idea, is that gravity is acting on all objects, and he eventually surmised too that every single object is also has gravitational attraction to other things, right? You are a center of gravity, and you are attracting everything around you to yourself in a very weak way, but it's still present everywhere. And in terms of what gravity is, that's something I don't know. I mean, what's causing it? I don't even know if physicists have a very good idea of where this is actually coming from and why there's this gravitational attraction, but it's kind of a fascinating area of science to read about. So we answered this question about why the moon does not fall like the apple did. And again, it has to do with this tangential velocity idea, right? That the moon has a directional motion, right? It's moving parallel to the surface of the earth. And so that's one form of force, right? This is physics, all about forces. But the reason that it's circling our planet is because Earth is also exerting a gravitational attraction to it. And so that locks it into the circular motion. What do we call this when an object is circling around another one?
Orbit.
Yes, so that is orbiting, where it is basically falling towards it, right? And what's interesting is you have to have these two things happening together. What I like about this diagram is over here, if Earth disappeared, what would the moon do?
Fly away.
Yeah, right. Its tangential velocity would continue, and it would just continue in whatever direction it was going. I kind of think about it like having a rock in a sling, right? That if that attraction wasn't holding it in that circular motion, it would then just shoot off. And I don't know where it would go. If it would head towards the sun, it's probably the next strongest gravitational force. It's kind of cool to think that planets, their gravity is powerful enough, they can actually even pick up things. Believe it or not, our planet, we actually picked up another satellite for a little while. You can read about this. There was a passing asteroid that entered into orbit around Earth because Earth's gravity was holding onto it for a bit. It rotated for a little while, and then it left again. And that gives us another thing that I know a little bit about, which is called orbital decay. Anyone want to guess what they mean when they say that the orbit is decaying? What does that mean?
It's getting weaker.
Yeah, right. And so it's actually getting closer and closer, right? That it could eventually fall in or hit whatever it is, right? That I guess the tangential velocity isn't quite strong enough to overcome the gravity here. Turns out, though, in terms of the moon, does anyone know, is the moon decaying in orbit, or is it actually getting further away from our planet? Anyone know? Yeah, it's interesting. I looked this up too because I wasn't entirely sure, but it looks like the moon is actually, I guess its tangential velocity is a little bit stronger. It's actually moving further and further away from Earth. Now, granted, this is like, on a scale of hundreds of thousands, millions of years. It's not anything you're going to see in your lifetime. But if the moon does eventually move away or fall away from Earth, it's going to have interesting consequences on a couple things. I don't know what the really obvious thing is.
It's gonna be like dark at night.
The
It'd be
tides.
very dark at night, right? We wouldn't get any sunlight at night. And you're right, yeah. And the moon offers light at night by reflecting it. And also, yeah, ocean tides. The moon's gravity itself actually pulls on our oceans a bit and gives us tides and helps with wave formation. And so the ocean, like current patterns, would very much change. So anyway, it would be very interesting if that happens. But anyway, if life exists on this planet at that time, I don't know. But kind of interesting to think about. All right, any questions so far on any of that? I hate to say it, but if we're moving into the realm of physics, it means we're going to go back to doing a lot of what? Anyone know what physics often involves?
Formulas.
Math, formulas. Yes, good times. So again, we kind of reviewed this in the Do Now quiz, but Newton came up with this gravitational force equation, and the whole point, they give you this crazy definition, right, that mass is directly proportional and the distance is inversely proportional. Again, what that means is if F is representing the gravitational force, then you're going to put mass on top. That's what it means by directly proportional. So if the mass of an object is really, really large, what's going to be true about the gravitational force? Is it also going to be large or small? If they're directly proportional.
Large.
Yeah, right? That's what that means, right? The larger the mass, the larger the gravitational force, which makes sense, right? Because the human body is not very large. We're not exerting a huge amount of gravity on things around us. Earth has a very, very high mass, right? And so Earth actually exerts a lot of gravity on things on its surface, which is why, when you drop a pen, it goes straight down to the ground. Distance is inversely proportional. That's why it goes on the bottom of the fraction. And as we sort of said earlier, the further apart objects are, what happens to the gravitational force between them? Is it stronger or weaker?
Weakened.
It's weaker, right? It gets smaller. And that's why when astronauts go into space and they're much farther away from the center of the Earth than we are, they experience a lot less gravity. And so that's why they seem to be floating around. So that's kind of the take-home message, right? Bigger objects exert more gravitational force, and the farther apart objects are, the weaker the gravitational force between them, right? That's the takeaway from this crazy-looking equation. There is something that's going to be added into this equation too, because right now it seems like, man, that would be a big value if you were just doing mass times mass divided by distance. I mean, that would mean even the gravitational force between me and my computer would be pretty significant, or at least a big number would come out. And if any of you read ahead, there is what's called the gravitational constant. It's capital G. And that's looking at the influence of the planet that you're on, right? Earth's gravity is very different from gravity felt on Mars or on the moon. And so this sort of puts it in context. It's a very small number, this capital G. It's like 10 to the negative something. But it kind of puts things on a proper scale, right? That it explains why your computer is not being gravitationally brought closer to you. Because the force that we experience is extremely small or weak. Okay, last thing to touch on is exploring this, what they call the inverse square law, which is just more on that same equation, right? That the farther apart objects get, the weaker the attraction is. This is just quantifying that, right? When they say the weaker the gravitation attraction, it is weakening by the square of the distance, right? That's what you have to divide it by. And so I know this diagram down here looks a little confusing, but think about this as a planet, right? If that's the center of the Earth, that's the source of our gravity. And then you can think of certain distances. So let's just pick a random distance. They're calling it R. Think about that as our one, right? That could be any distance. It could be 22 meters. It could be 3,700 kilometers, whatever number it is. But the point is, if you've got an object there, and then you've got an object that is twice as far away, so does everyone see how it's 2 times the distance? Then in order to calculate the gravity that's experiencing, again, you're just dividing by the square of the distance. So if it's twice as far away, we can just represent that as 2, right? So let's just imagine that we've got a distance of 1 to start off with. Well, then if I'm at a distance of 2, can anyone tell me what 2 squared is? What's 2 times 2? 4, right? In other words, the gravitational force is reduced by what? 1/4, right? So at twice the distance, you're experiencing 1/4 of the gravitational force. What if you were 3 times as far away? How would the gravity be reduced?
1/9.
1/9. Where did 9 come from? 9 came from doing what?
3 times 3.
3 times 3, 3 squared, right? That's literally the inverse square law. We can actually play with this, do a little activity using a couple objects that you should be able to get. So that'll be our next little activity. We're going to do something with our perspective, right? Because you can sort of light behaves in a very similar way. So we'll use our hands, and we're also going to use some dollar bills that'll have you get. So let me stop sharing this, and I'll have you all unmute yourselves so that you can ask for assistance or give me feedback. So let's all take ourselves off of mute. So I want to play with perspective to help explain this inverse square law, how things reduce by like 1/4 if they're twice as far away. So what I need you to do is take one hand and hold it close in front of your face, and take the other hand and try to put it about twice as far away, right? So you're doing something like this. Keep your hands relatively close together, but make sure you can see them both. And look with both of your eyes, so keep both eyes open. And the way I'm doing it, to be totally honest, does the hand that's further away, does it look like it's 1/4 the size? Be honest. Does it?
No.
Doesn't really, right? This is an eye thing, right? We have 2 eyes, which are very good at sort of trying to figure out exactly what's going on. So what you need to do is just close one of your eyes. So only look with one eye. And now, again, if you kind of play with the distance, does everyone see how you have like a little baby hand and a really big hand?
Yeah.
Yeah.
If you kind of work on the distance, you can make your distant hand look about 1/4 the size, right? Kind of goofy. But it's kind of hard to do with our hands, right? I want something that's a little more, like we can definitely say that we've got it to be 1/4 the size. And an easy way to do that is to find pieces of paper that are equal size, but that we can fold. And it turns out that money works really well for this. So what I need all of you to do right now is to go get two dollar bills or whatever else you can find that is of equal size, right? So if you got $1 bills, $5 bills, if you really want to show off, you can get $100 bills. But go ahead and try to grab two pieces of cash. They don't have to be the same value. They just have to be the same size, which all US money is the same size. Doesn't matter the value. So go ahead and go find two bills and come on back. I'll give you about a minute to work on that. So here's what we're going to do. I need you to take just one of the bills and fold it in half lengthwise. So you're making it much shorter, like that. And then fold it in half the other way, right? So this time go down. So you're doing like a hot dog fold and a taco fold or whatever, right? So you should end up with a little piece of money like that. In fact, what do you notice about the size of your folded bill compared to the unfolded one?
So 4.
It is 1/4 the size. So this is going to allow us to make a direct comparison. So now we're going to do the same thing. Hold the folded piece close to your face. Hold the unfolded one far enough away. And you want to try to get to that point where, again, looking through just one eye, you can get them to be the same size. If you put them right next to each other, it should work out pretty well. You can even hide the unfolded bill behind the folded one. Everyone seeing that? So what can you say about the distance of the unfolded bill being held away from your face compared to the folded one?
It's a quarter.
2 times away.
So you're holding it twice as far away from your face as the other one, right? So the folded one, the unfolded one is about twice as far away from your face, from your eye, as the folded one, but it appears to be 1/4 the size, right? That's the inverse square law in practice. And so gravity works the same way, that two objects, if one is twice as far away as the other, then that one is experiencing 1/4 of the gravity as it would have if it was half the distance from you. So this kind of helped me understand a little bit better what's going on with the inverse square law, what they mean by that, right? So if you got twice the distance, you got 1/4 of it. If you've got 4 times the distance, then it's going to be 1/16 of the gravitational influence. And we could play around with that. Like we could try to fold this 16 times. I don't know if you can do that. That's probably not good for the money. And plus holding it, 16 times or 8 times the distance from your face would be harder to do, but kind of helpful. So, all right, you can go ahead and put your money away somewhere safe. I now want to move on to another activity that I'm going to let you do on your own. So just to share my screen again, and we are now on task number 5 on that list of tasks for today. What you're going to do is you're going to watch a video that I made of myself demonstrating 4 kind of simple activities that I want you to do. It's through what's called Swivel. So when you click on that link, it should pull up this, and you can play the video there. However, if you can't get that link to work, or if you prefer to watch the video directly in this announcement, I do have a YouTube link embedded here. So you can just click play on that, and it should play right there in the announcement itself. So watch that video. It's a little over 4 minutes long. I'm doing 4 really simple activities to demonstrate gravitational force. You're going to need a cup that you can poke a hole in the bottom of. You'll need to be over a sink or a tub or outside where you can have some water splash. You'll need a piece of paper and a notebook as well. So let me know if you have trouble accessing any of that stuff. You don't have to film yourself or anything. I'm going to trust that you're going and trying these. I just want you to observe what happens. And I make kind of recommendations in the video. There's also 4 questions that I asked during the video, and that's what I want you to work on after you have completed these little demonstrations. The questions are in a discussion post, so that's the link that's on the very bottom right below the video, Science2F Exploring Gravitational Force Discussion. It will take you to a Canvas discussion post that looks like this. There are 4 questions, so I'd just like you, once you have tried the 4 little demonstrations and made your observations, just click reply and answer these questions as best you can. I'm looking more for your own thoughts, your opinions, and what you think you understand from the chapter. That's kind of the point of a lot of this. So I'll be sitting here the whole time, but if you want, you can leave this Zoom room to do the activities. And then once you're done, just come back. Let's say that I want to give you about 20 minutes. So let's plan to come back here at 55. So at 2:55 in 20 minutes. Plan to rejoin the room if you've left it, or you can just switch off your camera and mute yourself if you want, whatever you want to do. But if you've got questions, you can't find something to use or whatever, I am here, so just let me know. I'll be listening. Any questions right now? All right, go for it. I'll see you again at 2:55.